I will talk about basic modeling of strength properties. During recent years, great progress in the computational properties with quantum mechanics techniques have taken place. These procedures are also referred to as ab initio methods. For example, physical properties, elastic constants, and lattice parameters can be computed. Similarly, with the help of computational thermodynamics, which is called CalFAD, the composition and structure of phases can be calculated. This is basic information for the understanding of the role of the microstructure. Ab initio and CalFAD procedures are usually referred to as fundamental because they can make predictions without fitting to experimental data. For example, meaningful computations can be made even for systems that have not been studied experimentally. For mechanical properties like strength, ductility, and toughness, this situation is quite different. Models for mechanical properties are totally dominated by empirical approaches, where expressions are fitted to the experimental data with the help of a number of adjustable parameters. I've been inspired by the fast progress in the ab initio and the CalFAD fields to collect and develop basic models for mechanical properties that not rely on the use of adjustable parameters. Examples of some successful results will be presented. It's important to distinguish between basic and empirical models. Model of mechanical properties is totally dominated by empirical approaches, as I mentioned. Models that involve several adjusted parameters are fitted to the observed data. Often flexible mathematical expressions are involved, since they make it more straightforward to obtain a good fit. There are advantages with this sort of method. It's simple to apply. No special training is needed. A good fit to the experimental data is easy to obtain. But there are also disadvantages. With 3 or more adjustable parameters, many data sets can be described independently if the model is relevant or not. It's very risky to use such approaches to identify the operating mechanism. It's unsafe to extrapolate the result to new conditions, something that is practically always of interest. To extrapolate a parameter's dependence is very difficult in practice. It's not impossible to extrapolate from an empirical model. The basic requirement is that the number of experimental data points must be very much larger than the number of adjustable parameters. The rule of thumb is that the number of adjustable parameters should be less than the square root of the number of data points. To make the extrapolation work in practice, a number of additional requirements are needed. A basic model in this context is based on fundamental physical principles and involves no adjustable parameters. With such models, the operating mechanism can safely be identified, and generalization and extrapolation of the results can be done in a more precise way. Basic models are predictive. They can also be applied to systems where little or no experimental data are available. The starting point for many of the mechanical properties is a basic dislocation model. It consists of 3 parts. It's a work hardening part describing the continuous increase of dislocation density with increasing strain. But there are also recovery parts which takes into account that dislocations are interacting and annihilating each other. And there's a dynamic recovery part, which is strain dependent, and a static recovery part, which is time dependent. And with you add this, you get a strain derivative or time derivative for the dislocation densities. These formulations are fully equivalent. And this is valid for FCC metal, this approach. For BCC metals like ordinary steel, the situation is a little bit more complicated because you need more than one dislocation density often. The important thing to recall is that all the parameters here and the equations are derived from physical principles. So it's a well-defined model. The first example is for stress-strain curves. There are a number of empirical models, Holleman, Ludwig, Voice, and Swift, and so on. Only the Voice model is simple to derive from basic principles. You use the relation between the dislocation density and the strength through the Taylor equation. If you apply that in the basic dislocation models, you get more or less directly an expression for the stress-strain curves, which is equivalent to this Voice equation. And that equation works quite well in many cases. And here is an example for pure copper. The true strain is first shown versus true strain. And the data can be reproduced. A small detail here is that the static recovery part is negligible in this case, and that is directly evident from the figures. As in all my other results, no adjustable parameters are involved, so these are directly derived from the basic constants. The second property we will look at is stationary creep. Creep is a slow plastic deformation that takes place at constant stress, primarily at elevated temperature. The most important mechanism of creep is climb of dislocations, because the dislocation can then move also perpendicular to the glide plane. And here is a sample for a common 9-chromium molybdenum steel at 600 degrees C. We have a behavior here that we have a first of these curves, creep strain curves that we call creep strain versus time. We first have a decreasing creep rate. It's not very pronounced here. Then have a constant creep rate. And then finally you have a increasing creep rate. And these are referred to as 3 stages: primary, secondary, and tertiary creep. Secondary creep is also called stationary because then the creep rate is constant. That the primary creep can be very important can directly be seen from this curve where the strain rate is plotted versus strain. Then we can see that there's a pronounced primary creep as well. So the appearance of the curve depends on how you plot them. Now, the empirical model for stationary creep is the Norton equation. It describes the stress dependence of the secondary creep rate. It also takes into account the temperature dependence. And there are also so there are 3 adjustable parameters: the proportionality constant, the stress exponent, and creep activation energy. This equation can describe quite a number of experimental results. It's also possible to derive this equation, and here is the result. This can be obtained more or less directly from the basic dislocation equation, and all the parameters here are well defined. Most important part is probably the climb mobility, and this has been derived in the literature. And so that it's completely well defined. And using these expressions, you can describe the creep rate versus stress for pure elements here. Aluminium, oh, this is copper. We have nickel. It's strain creep rate versus temperature. So that you can see, you can describe these properties quite well. Now, if you move to an alloy, you have to take solid solution hardening and precipitation hardening from particles into account. And this has been in both cases, quite a classical problem. In fact, the slope of the curves has in the past been interpreted as a change in mechanisms. So some authors have suggested 3 or 4 mechanisms along these curves. Now, with these the new basic models, it's possible to describe all of the data with just one equation and one mechanism, dislocation climb. The situation for precipitation hardening has been even worse. People have worked for decades to derive equations for precipitation hardening. And they, meanwhile, they have used the values at room temperature. It's called Orwan strength, which describes bending around particles. Now, this, unfortunately, this overestimates the strength at high temperature quite a bit. Now, it's been assumed that you have to take into account the time it takes for the dislocation to pass the particles. And if you do that, you can describe a much better expression for the precipitation hardening. And here is an example demonstrated that it's quite possible to describe the influence of the cobalt content on this copper alloy, for example. It's also possible to describe the influence on temperature and other features. Now I move to a primary creep as the first phase of creep. Here is one model. There are several models, but here's one model how you can describe primary creep. So you, instead of the stress here, you replace it by this expression. And these parameters here are related to this, which are involved in the stress strain curve. And then you can see both from the experimental and the modeling results that you get a straight curve and a strain rate versus time in this double logarithmic diagram. And it's valid at high stresses, which I don't show, but it's also valid at very low stresses. And also, in a case for 600 degrees C, it's also valid in very low stress. And the interesting thing is you can use the same parameters at high stresses as at low stresses. And these represent an enormous extrapolation in the creep rate. And the same applied to changing the temperature. So it's many orders of magnitude extrapolation which takes place, and the model is still valid and demonstrates the validity of the model. The same applies to aluminium here. This is also a classical example. that which be quite confusing because people have thought that initially that the stress exponent was 1, and some people got another result. But now this can be fully explained because the stationary creep result is shown here. So most result obey that. But if you take primary creep into account, you can explain the low stress exponent here. And this is also illustrated here. The plot the stress exponent versus stress. You can see that at very, very low stresses, you can get a stress exponent of 1. Otherwise, you get a stress exponent of 3, which is typical of more stationary conditions. You can extrapolate the results also in this case by many, many orders of magnitude, and the results still work because, as you saw previously, the aluminium model can be used at the room temperature and at high stresses. So it verifies the validity of the model. I come to my conclusions. It's been demonstrated that basic models can be formulated for a number of mechanical properties without the use of any adjustable parameters. Many classical results are now possible to explain with the help of the basic models: solid solution hardening, particle hardening, creep stress exponents, creep at very low stresses. The basic models can be used for a wide range of temperatures and stresses, verifying the general applicability of the models. We are obviously at the beginning of a development, and hopefully many more can be engaged to formulate more basic models.